Hello everyone. In this video, we are going to do a quick introduction to vectors in 3D space, which share a lot of the properties of vectors we've already studied in 2D space. So we'll get started and we'll finish up 3D vectors in another video. All right, so 3D vectors are working in 3D space where we have three axes. First, we have the x-axis, which we could draw diagonally like this. X. We also have the y-axis, which we could draw diagonally like this. Y, so it's kind of like we have a flat plane. Finally, we have the z-axis, which is going vertically up, like that. So this is C. And the positive parts of each axis are going to be closest to us. So Z, we have +1, +2, +3, and so on. For Y, same deal, +1, 2, 3, and X is also going to be 1, 2, 3, and so on. So we should think of this as Z is vertical, and we're looking down at the X and Y axes. So we have three axes, which means we also have three planes. The first plane we can look at is the XY plane, which is the plane right here. So the plane containing the X and the Y axes, so we're looking down on the XY plane. We can also consider the ZY plane, which is the plane here. So kind of like to our right, we have the YZ plane. And then finally, to our left, we have the XZ plane over here. This is the XZ plane. So we have three planes, and planes are just a collection of two axes. For example, in 2D space, we always are working on the XY plane. We can represent planes with equations. And we can do that by first looking at the XY plane. The XY plane are all combinations of X and Y where Z equals 0. So the equation Z equals 0 gives us the plane that covers the XY plane. For the YZ plane, X equals 0. For the XZ plane, Y equals 0. So these are the equations for these planes. When talking about specific points in space, instead of an ordered pair, we're going to have an ordered triple. For example, this point here, right at the 3 on the y-axis, has an x value of 0, a z value of 0, and a y value of 3. So 0, 3, 0. Up here, 3 on the z-axis, 0x, 0y, 3z. Down here, 3 on the x-axis, 3 for x, 0 for y, 0 for z. So we have x, y, z for our ordered triples. If we consider a point on the xy plane, for example, 2, 2, or let's do 2, 1. This point here on the xy plane is going to be 1 for x, 2 for y, and it's on the xy plane, so z is 0. We could also consider points in space, for example, 2 for y, 1 for x, and then 2 for z. So this point up here in space, so it's not on any of our three planes that we defined. Here we have an x value of 1, a y value of 2, and a z value of 2. So this is how we describe points in 3D space with an x, a y, and a z coordinate. So let's consider another point in 3D space. Let's stick with 1 for x, 2 for y, and then we're looking at, these dashed lines are just kind of like guides to help show you where this point is. We're looking at 3 for z. So we have a point up here that's close to us. This point is 1, 2, 3. When we talk about distance, we're looking at distance from the origin. The origin is still the point right in the middle here, where all of our axes meet, 0, 0, 0. And when we talk about distance, we're looking for this distance right here. So the distance from the origin. And define distance, we can think about our distance formula in 2D space, and we just extend it to include another axis. So how this works is if we have a point and we're looking for the distance to the origin, for example, 1, 2, 3, our distance is going to be the square root of x squared plus y squared plus c squared. So square root of 1 squared plus 2 squared plus 3 squared. So our distance to the origin of this point is going to be the square root of 14. That is our distance. If we're looking for the distance between 2 points, let's call them P1 with coordinates x1, y1, z1, and P2 with coordinates x2, y2, z2. We are looking at our distance formula, and in order to find the x, y, and z values, we find the difference between the x, y, and z points. So we would start off with x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. So very similar to our two-dimensional distance formula, we're looking for the difference between the x values, y values, and z values. We square them, add them up, take the square root. We can represent vectors in space using a similar notation to two-dimensional vectors. For example, if we have a vector from the origin going up to the point that we defined earlier, so if you have a vector here from the origin to the point 1, 2, 3, we can write that as, let's say, v is equal to 1i plus 2j plus 3, and then for the z direction, we'll use k. So 1i plus 2j plus 3k. So we are looking at our x component here, y component, and z components. If we have a vector in 3D space, so for example, let's consider our white vector here from point 1 to point 2. So x1, y1, z1 to x2, y2, z2. And we want to rewrite this so that it starts at the origin. Maybe it's a little bit easier to work with if one of our points is 0, 0, 0. What we can do is rewrite it in a way we're kind of like moving it down here to the origin, starting here, ending here. We could call this vector v. And the coordinates for v are just going to be the differences between x, y, and z. So v in this case is just going to be x2 minus x1 I plus y2 minus y1 j plus c2 minus c1 k. Here I've listed a few of the properties that we have for three-dimensional vectors, and these are very similar to the properties we have for two-dimensional vectors. So I'm not going to spend a lot of time on them. We just have equality up here, a1, b1, c1 equal to a2, b2, c2. If we add vectors, we add them by components, or we can't add them by If we add vectors, we add them by components. So we could add the a's, the b's, the c's, and so on. If we subtract, we're just subtracting instead of adding. Multiplying by a scalar, we can multiply each component separately by that scalar. And finally, the magnitude of a three-dimensional vector is just going to be very similar to our distance formula, where we're taking the square root of the three components individually squared and then added together. And again, similar to two-dimensional vectors, the unit vector in the direction of v is equal to the vector v divided by its magnitude. And this tells us that we could also write v in terms of the magnitude of v times the unit vector. Next, looking at the dot product, so slightly more recent material. The dot product between two vectors, if v is a1 I plus b1 j plus c1 k, and another vector, we could call it w, is a2i plus b2j plus c2k. The dot product between v and w, so one way we can find multiplication between these is equal to, and here, similar to two-dimensional, we can just multiply the components separately. And again, we end up with a scalar in this case. So we don't have the I, the j, the k. We're just multiplying the values, the number values of the components. So two vectors multiplied together give us this value as a scalar. The other definition for dot products also holds, where we have the dot product between v and w is equal to the magnitude of v times the magnitude of w times cosine of theta, the angle between those vectors. And again, we end up with a scalar on this side. So all of this information can be found in the book. I just wanted to go over a quick overview of what vectors in 3D space look like. As I mentioned, most of these properties are very similar to two-dimensional vectors. In our next video, we're going to finish up vectors in 3D space, and then finally, we're going to finish our unit with the cross product, so the other definition of multiplication, which I think will be pretty fun.